Hello, today we are going to be talking about glaciers, which are really just flowing rivers of ice. They are ice and snow moving downhill like a river. It sounds weird to picture a river of ice, but that genuinely is what's happening here. And glaciers do a lot to shape the land. We've been talking a lot about weathering and erosion and deposition, and a lot of that is really clear when you see the effects of glaciers both because they carry rocks and boulders with them. Glaciers can erode the landscape by carrying things away. And also, ice is really good at scratching and weathering and breaking things down. So glaciers shape the surface the same way rivers do, or the same way wind can, and they can change the way rivers flow. They can carve out new lakes. They can carve entire mountains. They have a huge impact on the land. And they form by the accumulation of snow that compacts as it continues to fall. So let's look at the parts of a glacier. I'm going to tell you them and then show you a diagram. First, there is the zone of accumulation. This is towards the top, typically where new snow is falling. This is lighter, less dense. Snow is just falling up here. It's like the start of the river. The zone of wastage, or sometimes called the ablation zone, is like the bottom or end of the river. And this is where the snow has melted and compacted and refrozen so many times that it is now more ice. This is also where, as the glacier moves forward, it can be melting for good. And the snow line is a line in the middle where freshly fallen snow is transitioning into this compact glacial ice. So here's what all of that looks like. We've got our zone of accumulation at the top. New snow is falling. It is light and airy up here. Down at the bottom, you can even see it gets dirtier as it's picking up sediments as the glacier moves down, and it is much more compact now and ice. You can even see it's melting down at the bottom. And we've got the snow line kind of in the middle where the freshly fallen snow is transitioning to this compact ice. So how does snow become ice like this? It melts and refreezes and melts and refreezes. And each time it melts and refreezes, it gets closer together. It loses some of the air in the middle. So we start with our nice pretty snowflake that melts a little bit and refreezes. So it's a little bit more granular, a little bit smaller and less easy to identify. It melts and then refreezes a little bit more to become fern, which is an important middle step. And then lastly, it melts and refreezes again to be just a hunk of ice where you can see there's barely any air left. So this is incredibly compact. This isn't a snowball. This is an ice cube. You probably have before heard people talk about ice sheets or maybe ice caps. Those are similar to glaciers, though they are a little bit different. An ice sheet is specifically a glacier that is bigger than 50,000 square kilometers. Right now, that is only Greenland and Antarctica. In Earth's history, there have been other ice sheets during ice ages, but right now we just have the two in Greenland and Antarctica. Ice caps, you maybe have heard people talk about polar ice caps before. Those are similar to ice sheets, just smaller. And an ice shelf is part of a glacier in that ablation zone that is in water. So a glacier is over land, and an ice sheet, additionally, is over land. So when ice or snow from a glacier makes it to the ocean, it will increase the sea level. Sea levels will rise. Ice shelves are already in the ocean. So whether they are frozen or melted, it is not impacting the sea level because it is already there. When this mountain glacier falls down the side of the mountain and makes it all the way to the ocean, that will cause sea levels to rise. If more of this ice sheet moves into the ocean, that will cause sea levels to rise. This ice shelf or this sea ice or this iceberg melting will not affect sea levels because they are already a part of the sea. I said as the glaciers move down, glaciers do move. They are flowing. They are like rivers. So when a glacier is flowing downhill, there is more snow accumulating faster than it is melting, we say that the glacier is advancing, it is accumulating. There is more snow falling, enough to keep pushing it downhill, so the glacier is moving forward. Other times we talk about a glacier retreating. It does not flow uphill. It is not that something is pulling the glacier back. What's actually happening is that the snow and ice at the bottom is melting faster than it can be replaced, faster than new snow is falling. So this isn't flowing uphill, it is retreating, but that is because things are melting faster than there's new snow. So this is also called ablation. Glaciers carve out a lot of really interesting things, and we can look at features from erosion and features from deposition. So first, erosion. These are features that get carved out as the glacier, the ice carrying rocks, moves down the side of a mountain. The first is a cirque. This is a bowl-shaped carve-out. This is just a chunk missing out of the side of a mountain. Then we have, I know I'm going to pronounce this word wrong because I've never fully understood how to read this accent, but what I say is an arête. This is a ridge that is left behind. So you can think of it like a line of mountains, all one, a ridge that is surrounded by cirques, these carve-outs. And then you've got a horn, which is a pyramid peak that is left behind by everything else. It is a spot where cirques have carved away all of the sides of the mountain, and you are left with this peak just standing out on its own. Matterhorn in Switzerland is probably the most well-known or best example of one of these glacial horns. Other features that exist because of this erosion include a glacial trough. This is the valley that is left behind that a glacier carved out, and it has a distinct U shape to it. A hanging valley. Lots of times with glaciers, you've got like a main big glacier, but then some smaller ones that feed into it, the way you can have smaller rivers that feed into a big river. So a hanging valley is a small valley left behind from one of those smaller glaciers that feeds into the main one. And a fjord is what happens when a glacial trough meets the ocean. If you've seen Frozen, and they talk about fjords, or in Scandinavia, there are lots of fjords, which are places where the valley meets the sea. So this is an example of what it looks like while there is a glacier. Here is our main glacier that is flowing downhill, and we've got lots of smaller glaciers that feed into it. And you can start to see some of these erosional features like the cirques, the ridges that are arêtes, and the horn. And then once the glacier has retreated or fully melted, here is that very clear glacial trough, that U-shaped valley. And there are all of these hanging valleys, smaller glacial valleys that feed into the main one. It really is a very clearly U shape. This is a town in Colorado that was formed from a valley, or formed in a valley that was carved by a glacier. So there are ridges, arêtes on either side, and you have this U-shaped valley where there was once a glacier. There are also features from things getting dropped off. Remember, deposition is dropping things off, and glaciers carry rocks and ice and dirt with them, which means they're going to drop dirt and rocks and ice off as they go. And there are a couple of different features that we can see all over the world from this. The first is what is called a glacial erratic. This is a boulder in the middle of a field, a giant rock where you wouldn't expect to see a rock. A glacier somewhere along the line picked up this large rock, but then the ice melted and the boulder just fell and was left there. So these are giant boulders, large rocks that you just don't expect to see where they are because they were being carried by a glacier and then just randomly dropped. Then we have moraines. These are ridges of till or dirt and sediments that glaciers are pushing in front of them or next to them. There are three main types of moraines. end, or sometimes called terminal moraines, are all of the dirt in front that the glacier was pushing in front of it. So it's this little tiny hill of dirt at the very front of a glacier. Lateral moraines are piles of dirt on the side next to the glacier that get pushed up over time. And lastly, there are medial moraines. These form in the middle of a glacier. When you have two glaciers come together, they join. So here I've got two different glaciers that, after they got around this rock, combined. And the lateral moraine, the ones on the side, on the outside, are now suddenly in the middle of a new, bigger glacier. So a medial moraine can form in the middle of a bigger glacier. We can see these things left behind when glaciers move. So here are a bunch of erratics. They don't all have to be giant boulders, but these are things that are in places we wouldn't expect them to be because they have just been left behind after the glacier has retreated. We can also see scratches, carvings in rocks, but naturally the rocks carried by the glacier or the dirt and sediment being pushed on the sides of the glacier, those moraines, will carve into rocks as they pass by. And you can see all of these lines of where dirt and sediments were dragged along the side of this rock. Other deposits by glaciers, a kettle lake is a bowl-shaped depression left when glaciers retreat. So a chunk of ice will get stuck in a hole in the ground or will fill in a spot in the ground. Eventually, all of this ice will melt, and you're left with a pretty clearly bowl-shaped hole in the ground. Lots of the time, these become lakes. The Great Lakes, Huron, Ontario, Michigan, Erie, and Superior, are believed to be giant kettle lakes, exactly like this, that formed because of glaciers. Next, there is an esker. This is a long, winding ridge of sediment that forms under the glacier. If you find a spot under a giant ice cube where a little river can form underneath, something has broken through enough to melt under the glacier, then sediment will fill that in, and you will get these little, almost like winding rivers of dirt under the glacier. Then the glacier all retreats or all melts, and all that's left behind is this ridge of sediments from the stream. They can be pretty big. I mean, here is a house or a person for comparison. So if this is a little ridge under a glacier that is the size of a house or this tall compared to a person, imagine how big the glacier had to have been then. Glaciers are typically huge things, miles wide, a mile or so deep, miles and miles long. They are massive. Other deposits, we've got a drumlin. These are a bunch of kind of streamlined hills that all form parallel to each other when glaciers advance and retreat and advance and retreat. Lots of times glaciers will move a lot in a single season. They will kind of cycle through advancing and retreating over and over again. So these are deposits of till or soil and sediments that have been reworked over and over, glaciers advancing and retreating over and over, get all of these very streamlined hills. Next, we've got a tarn. This is a mountain lake that forms in a cirque. So remember back at the beginning, a cirque is a bowl-shaped cutout on the side of a mountain because of a glacier. If that gets filled in, it is a mountain lake that we call a tarn. If there are a bunch of them all together, we often call groups of tarns a paternoster lakes. So this is a lake on the side of a mountain that was carved out by a glacier. We can see a bunch of these things all in one place. So here is a retreating glacier. Remember, it's not moving uphill. It's just that this ice is melting before new ice can push it forward. But we've got this little esker, that winding ridge of sediment. Here is a drumlin field where it was reworked over and over, just piles of dirt. Here is the terminal moraine. This was all of the dirt that was being pushed in front of the glacier, and we've got some kettle lakes there as well. So I said that the Great Lakes were an effect from glaciers. There has been recently, or fairly recently, an ice age. It ended about 18,000 years ago, and the ice reached as far south as Nebraska. So 18,000 years ago, when there were more glaciers and more ice sheets, this light blue line shows what the coastlines looked like then, when all of that ice was on land, when it was on top of North America. So you can see we've got a really wide Florida. Most of the East Coast extends farther out. The black line is the current coastline, and then this gray or green is what the coastline would be if all of today's glaciers were to melt and join the sea. So if all of the ice that is currently making up glaciers in Alaska, and there are glaciers on every continent. So if all of these glaciers were to melt, then this would be our new coastline. My geography of Texas isn't great, so I think maybe we would get to become a coastal town, but Florida's gone. Much of the East Coast gets a little bit cut off. Uh, California gets a couple more lakes and such. But so there's currently a lot of water tied up in ice. And here it is a little bigger to see what it was during the last ice age, what it currently is, and what the coastline would be if all of the current ice sheets melted. If all of the ice in Antarctica melted, where would we be? So I said all of this happened during an ice age. This is the ice age that the ice age movies take place during. It is the most recent ice age that covered about 2 million years, and glaciers advanced and retreated like 15 to 20 times. So again, it was very cyclic. Sometimes they're moving forward because there's new snow, and sometimes they are retreating because snow is melting. All of those different features, moraines, erratics, those random rocks left places, all of those things are found throughout the US as far south as Nebraska. They're in New Jersey, they're in the Dakotas, they're in Illinois and Indiana. These are features that we can see which prove that there was once an ice sheet that covered much of North America. It started, or as recently as 2.5 million years ago, and was part of this ice age that lasted until 18,000 years ago. And so it was this massive glacier that covered all of Canada and much of the US. Again, lots of retreating and advancing. So it would move south a little bit, and then it would be too warm and the ice would melt and it would move, it would look like it is moving back. Then it would some more snow would fall and it would advance and move forward again. How did we end up in an ice age? What happened? There are two main theories. One is that plate tectonics changed land and ocean locations, which messed with ocean currents, which messed with the weather. But the second, and the one we'll focus on, is that changes in Earth's orbit affected how much heat we got on the surface. That's based on three factors that all have to do with the geometry of Earth. So there are some slight variations that we can observe and calculate in how Earth moves around the sun. The first is the shape of our orbit. We don't orbit the sun in a perfect circle. It's kind of a little bit more like an oval, but that shape can actually vary just a little bit, and that is called the eccentricity. How circular is the orbit, or not circular? The second is how tilted are we? We learn in school that we've got a 23.5 degree tilt on our axis, but that can actually wiggle a little bit, which is called the obliquity. And lastly, Earth, as it revolves on its axis, kind of spins like a top. And so our North Pole points in a different direction sometimes, and that is called precession. All of these things are things that we can measure and observe, and they all affect how much heat and how much sunlight the Earth gets at a time. Sometimes we get more heat, other times it's less. And these conditions can all kind of stack on each other. So if we're not getting a whole lot of sunlight, that's when you're likely going to get an ice age. We call these Milankovitch cycles after the guy who kind of pieced this all together. So precession, the wobbling like a top, is a cycle that goes around every 20,000 years or so, where the North Pole is pointed in a slightly different direction. So our North Star is different than the ancient Greeks' North Star. The second was obliquity. How much of a tilt do we have? Right now, we are kind of right in the middle at this 23.5 degrees, and this cycles about every 41,000 years. And eccentricity, how circular is the orbit, or how elliptical is the orbit. And this actually has two different cycles. One of them is 100,000 years, and one of them is 400,000 years. So you can see trying to line all three of these things up in just the right way isn't going to happen very often. But when it does, you're going to have huge effects on the temperature of Earth based on how much light we are getting. And so if everything lines up perfectly, like it did 2 million years ago, then you're going to end up, or you could end up with an ice age. That is the theory behind these Milankovitch cycles. Bye-bye.